Welcome back to this lecture on recursive algorithms. In this last segment, we're going to analyze the time complexity of the merge sort algorithm. So this algorithm takes as input an integer sequence to be sorted. So let n be the size of that input sequence. We're going to assume for the analysis that n is a power of 2. Remember that every time we call merge sort recursively, we do so on a sequence that is about half the size of the original sequence. So if n is a power of 2, every time you cut it in half, every subsequence is also a power of 2. So we get an integer every time all the way down to the base case. Now this assumption doesn't make a difference in the analysis other than it makes the mathematics simpler. If n is not a power of 2, the analysis is still going to carry over, but it's more complicated because you have to use rounding in the computations. So n is a power of 2 from now on, and let f of n denote the worst case time complexity of merge sort. So what we're trying to find is an expression for f of n. Now let me put up the pseudocode description of the merge sort algorithm that we discussed on the previous segment. Now, a natural question would be, why are we looking at the worst case time complexity? It looks like at this level of description, there aren't any differences between the best case and the worst case, because merge sort always does the same amount of work for a particular value of n. If n is 1, you always do this. If n is greater than 1, you always do this, and there's no while loop of if statements in there. So why are we talking about the worst case time complexity? Well, the reason is because, remember, the merge algorithm has a worst case time complexity that is worse than its base case time complexity. So of course, the worst case for merge is going to create also a worst case for merge sort. So here, we're going to focus our analysis on the worst case time complexity of merge sort. So let's look for an expression for the runtime of merge sort, which remember we denote by f of n. Notice if n is equal to 1, the runtime is trivial, it's just constant time to do this part. So let's just ignore this part completely and focus on the case where n is greater than 1. How much work does merge sort do? Well, it has to perform these 4 operations here. So f of n is going to be the sum of the amount of work for each one of these operations. So the first one is an assignment statement with simple arithmetic operations. Let's call that constant time operation. Let's say it takes 1 unit of time. That's the easy one. Now, the question is, how much work is performed by this line in the algorithm? Well, this line is essentially a recursive call to the same algorithm, whose runtime is given by the function f. So, the worst case time complexity of this line is going to be f of what? Well, it's going to be f of whatever length of the sequence is passed into merge sort. And that sequence is exactly of length n over 2. So in other words, the amount of work for this recursive call is f of n over 2. Now, of course, we can make a similar reasoning for this line, since the sequence that you pass into the second recursive call has also length n over 2. So here is another f of n over 2 term. And finally, the fourth operation is a call to the merge algorithm. Remember that the worst case time complexity of this algorithm is big O of n, where n is the length of the input, which is the sum of the length of L and the length of R. Or what's the total length of L plus R? Well, it's exactly n. So the runtime of this operation is big O of n. We're just going to write it down as plus n. Even though there's a constant here, it's not going to matter in the end. Now that we have an expression for f of n, let's try and simplify it. First, let's group together the n and the 1. Clearly, the rate of growth of n plus 1 is the same as the rate of growth of n, which means the constant 1 doesn't matter here in a big O analysis. So let's ignore the 1. So we can finally rewrite f of n as 2 times f of n over 2 plus n. This is our recursive definition for f of n. We're going to use it repeatedly, so let's record that on the side here. So, what do we do next? Well, what we would really like to get is a closed form formula for f of n, not a recursive definition. So we're going to use the iterative method to replace this term by, so what is f of n over 2? It's whatever you get here by replacing n by n over 2. So we're going to get 2 times f of n over 4 plus n over 2. Let's perform the substitution right here. And then let's multiply out the 2, so we're going to get 4 times f of n over 4. And notice 2 times n over 2 is n, plus n is equal to 2. So this is still a recursive definition of f over n, of course, so we keep working on our iterative method. We're going to rewrite this expression by replacing f of n over 4 by, so you put n over 4 here, you're going to get 2 times f of n over 8 plus n over 4. Then you multiply out the 4, you're going to get 8 times f over n, 8 times f of n over 8, plus 4 times n over 4 is n, plus 2n gives us 3n. Now I'm going to stop here, since I can see a pattern emerge. Now if you don't see the pattern, I encourage you to go a couple more times and see what happens. But the pattern is basically you see a power of 2 appearing here and here. And not only that, the power of 2, which in this case is 2 power 3, you can see that that power of 2 is also the integer that appears here in front of the n. So if you keep going, you're going to get a pattern like this one, which is 2 to the power k times f of n over 2 to the power k, and this k is going to be in front of the n as well. So, what happens here? Notice every time we go to the next step, the argument to f is divided by 2, which is why we have a power of 2 in the denominator here. But remember, n is also a power of 2 in our assumption. So what happens when you keep dividing n by 2? Well, eventually, this fraction is going to be equal to 1. So you're going to have k of n doesn't change, and you're going to have an f of 1 here. Now, when does that happen? Well, this fraction is equal to 1, obviously when n is equal to 2 power k. In other words, k has grown large enough that 2 power k is equal to n, which means this number right here is nothing but n. And of course, we know that f of 1 is the runtime of merge sort when the input sequence has size 1. And this runtime is a constant. Let's call it 1. So the final expression for f of n is n plus k times n. Well, actually, that's not really the final expression because we don't know what k is. So let's think about k for a minute. What is k? Well, k is the power of 2 that's equal to n. Remember, n is equal to 2 power k in our analysis. So, what's the value of k? Well, I just said it. K is the logarithm base 2 of n. So in conclusion now, we can replace k by its expression here to get f of n equals n plus n log base 2 of n. And of course, in big O terms, this n log n dominates the linear term here. So in conclusion, f of n is big O of n log n. And that is the worst case time complexity of merge sort. And the remarkable thing here is that in a worst case, this algorithm is much faster than bubble sort or insertion sort. Remember, those had a big O worst case time complexity of n squared, and n log n is a lot faster than n squared.